This one. Okay, so I'm glad that I helped you do for the homework on the website. And if you have any other question, you can please feel free to ask me during the break. Uh, no, right? Okay. If no, we can continue with the example. So in this example, we are considering like the Seagate hard drive model has a failure rate of 2.89% in a year. And we are considering the first problem here. If your computer has only, let me move, only the Seagate hard drive model ST4000, what is the probability that it will work for a year? So let's do it together. The failure rate of 2.89% converts to a probability of 0. Let me write here. Where is the pen? Oh, it's here. Of 0 0.0289, right? Because you divided it by 100. If you convert it, so the probability that the hard drive will not fail during the year is found as follows. Will not fail. That is the like P of at least one hard drive does not fail, right? One hard drive does not fail equals one, based on the formula that we studied earlier, P of A bar equals 1 minus P of A. So if you call the probability, the event A is the event for the failure, then the event A bar here is at least one hard drive does not fail. So you have 1 minus P of failure. Oh, I'm gonna mute Andrew here. So in this case, we have 1 minus P of failure. It's gonna be 0.0289, and then the final answer will be 0.971, right? So that is the probability that it will work for a year. Are we good? So in this case, we are using the complement event. And B, if your computer has two Seagate model hard drive, in A we just have only, right? But here we have two. What is the probability at least one of them will work for a year? So what do you think? So in this case, let's do it. Let me clear the first problem, and then I'm gonna write the second answer here. So with only one hard drive, there is a 0.0298 probability of the failure, right? But with two independent hard drives, there is only a remember in the first problem, when you calculated the probability that it will work for a year, you can get 1 minus point um, 0.289, right? 0.289, so it gives you 0.971. Okay, so for the second one, two independent hard drive, the computer will work if both hard drives don't fail. So in this case, the computer will work if at least one of the hard drive works. Do you agree with me? So in this case, P of at least one hard drive does not fail equals 1 minus probability of both hard drives fail, right? So they, because they are the complement, they are complement. Oh, let me, both hard drives fail. Okay, so what is the probability of both hard drives fail? If you remember the formula for the multiplication rule, right? In this case, you can use the multiplication because both both hard drives fail, and they are we can consider they are independent. So we have 0.0289 times 0.0289, and the answer is going to be 0.999. So that is the answer for B, right? So in this case, what is the interpretation that we should make for the conclusion? When you are done with the calculation, you have not done the problem yet. You have to make the write the interpretation for the probability, right? So in this case, with you can say with only one hard drive, there is a 0.0289 probability of failure. But with two independent hard drives, there is only a 0.001 probability that the computer will not work with at least one operating hard drive, right? But using two hard drives instead of just one, the risk of failure decreased by a factor of, in this case, the how do you fight? By a factor of, in this case, please remember the failure rate is 2.89. So if you use two hard drives instead of just one, the risk of failure decreased by a factor of 1 over 28.9, right? Based on the formula. And then by using two independent hard drives, the risk of serious failure is dramatically decreased, and reliability of the computer is dramatically increased. So the redundancy at work. Yeah, that is an example for the Seagate hard drive. So we are good with this one, right? And then for the summation, for the addition rule and multiplication rule, that I give you, I gave a lot of examples for the addition rule and multiplication rule. You can watch the video, the previous video. I'm going to share both videos on the lecture section on our website, and then you can see that again, right? Please remember, if you do the addition rule, like the word or suggests addition, and when you add P of A and P of B, we must add in such a way that every outcome is counted only once by subtracting P of A and B, right? Because like all the common thing, you can remove them. In the multiplication rule for P of A and B, please remember that we will do, the formula will be P of A times P of the event B occurred, given that the event A already occurred. And then this is called the conditional probability, right? Okay, so let's let's have a little break here, like 4 minutes, and then we can continue to the section 4.3. Are we good, everyone? Okay, so 3 minutes for the break, and then we can continue with 4.3. Okay, so we are back with section 4.3, right? Complements and conditional probability and Bayes theorem. Do you see? Maybe yeah. I said that we have 3 minutes break. Okay, so I'll give you a little bit more time. Yeah. Okay, so we can get back to work, right? Complement and conditional probability and Bayes theorem. As uh, I discussed earlier about the conditional probability in the previous section, I gave you the example related to drawing cards from a deck, right? If you draw one card from a standard deck of 52 cards, let's say in the event A, the card is a king, and the event B, the card is a face card. Let's say a jack or a queen or king, right? So what is the conditional probability that the card is king? Okay, the card is, let me write down here. The card is gonna be king, given that it is a face card. Okay, so B here is gonna be the face card, and A here is gonna be the card is king. Now let's find the conditional probability in this case. So for the total number of face card in this in the deck of 52 cards is 12, right? And the number of kings, we have four kings. So now if you want to, so among the face cards, 4 out of 12 are kings. So you have the this is the probability of getting a king, given that you draw them among the face card. Okay, so 4 over 12, which is 1 over 3. Are we good? So this is the conditional probability. And then I'm gonna go back to the main definition, right? So we extend the use of the multiplication rule to include the probability that among several trials, we get at least one of some specified event. We consider conditional probability the probability of an event occurring when we have additional information that some other event has already occurred, and we provide a brief introduction to Bayes' theorem in this section. Let's see, when finding the probability, let me erase everything here. When finding the probability of some event occurring at least once, we should understand the following. At least one has the same meaning as one or more. And the complement of getting at least one particular event is that you get no occurrences of that event. Do you have any questions so far? Let me check the chat to see if you have any questions. Please feel free to interrupt me at any time, okay? Now let's see the probability of at least one. Finding the probability of getting at least one of some event. Let A is the event of getting at least one of some event. Then A bar is getting none of the event being considered, right? Then can you maybe we can do an example here. me give you an example. So let's consider the example related to tossing a coin 3 times, right? What is the probability of getting at least one heads in 3 coin tosses? So let A here is like getting at least one heads, right? A is the event of getting at least one heads, and A bar is the event of getting no heads. Do you agree with me? Getting no heads. Okay, so that means like for the event A complement, it's gonna be all tails. Now the second step, we use the complement rule. That means P of A here is at least one heads, right? Equals 1 minus P of A bar. That means like no heads. So we calculate P no heads. Probability of tail no heads here. That means tail. So tail, you have like, okay, when you toss one coin, you just have one half, right? Because you have 2 chances, head or tail. And if the probability of getting a tail is going to be one half, and then you have 1 minus one half, it gives you, wait, is it correct? No. The reason is we have 3 coins. I should write, we are tossing 3 coins. Do you agree with me? So no heads here, you have to do like no head for 3 coins. So you have 3 times. It's going to be 1/8. And it's going to be 0.125, right? Am I right? 1 minus 0.125. It gives you 0.875. So this is the probability of getting at least one heads when you are tossing 3 coins. So are we good with the probability of at least one? Good, right? Okay, no questions. Yeah. Let me erase this one and then we can move to the next one. The probability of at least one here, finding P of A bar equals the probability that event A does not occur. Okay, subtract that from 1. These are just all the steps, right? And then now it's your turn. Let's do this example, manufacturing. A factory of the global manufacturing company was manufacturing products with a defect rate of 15% based on the data from Harvard Business Review. If a customer purchases 12 of the products, what is the probability of getting at least one that is defective? What do you think? So we will use the 4 steps that we just studied above, right? The first step, so let A is the event of at least, let's see, a customer 12, and what is the probability of at least one that is defective? Okay, so now A is the event of at least one of the 12 products is defective. Do you agree with me? At least one of the 12 products is defective. Okay, so now step 2, we see that the event, the complement event A bar, that is going to be not getting at least one defect among the 12 items, right? That means all 12 items are good. Do you agree with me? With no defects, right? No defects. Now let's find the solution here. So if you want to find the probability of A bar, is gonna be the probability of all 12 items are good. Do you agree with me? So the probability of having 12 items that are good is gonna be, okay, so you can use the multiplication rule here. the first item that's good is going to be here defect rate 15%. That is equivalent to 0. Wait, 15, because you divided it by 100, right? So when you find the rate for the one that is good, it's going to be 1 minus 0.15, it's going to be 0.85. Are we good? 0.85. So 0.85 for the first item, that's good. And then since we have 12 items, so you need to multiply it by 12, multiply this number 12 times, and it gives you 0.142. So that is the probability of having all 12 items that are good, no defects at all. Now, the last step, if you want to find the probability of A, it equals 1 minus P of A bar. And then you just need to do the subtraction. And we are done, right? 858. So that is the final answer. Are we good, everyone? Any questions or comments so far? Okay, if no, let's clear this one on my drawing. So the next one that we are going to consider is the conditional probability. A conditional probability of an event is a probability obtained with the additional information that some other event has already occurred, right? Like I gave you the example earlier. And then you can use this notation to denote that this is the conditional probability of event B occurring given that event A has already occurred. So you write like A already occurred on the right side and then B here on the left side. The intuition. The conditional probability of B occurring given that A has occurred can be found by assuming that event A has already occurred, right? And then calculating the probability that event B will occur. As you can think about like the example related to the deck of cards that I gave you earlier. And the probability, in this case, you can use the formula, like this is the conditional probability of like for the event B occurs given that the event A has already occurred, it equals P of A and B divided by P of A. Now let's maybe before doing the drug calculation, maybe let me think about an example. Let's do an example for this formula. So what do you think? Maybe let's do the example related to the card. It's going to be easier than this one, and then we can move to this one. Okay, let me erase it here, and I'm going to give you the quick example related to the deck of cards. Like drawing a card from a deck, right? Again, we still have a standard deck of 52 cards. So the event A now, the card is a face card, right? So you have 12 face cards. Event B, the card is a king, so you have 4 kings, right? And A and B, the card is a king. That is also a face card because you have the event A and B. That means like you must have a face card with the event B happen. That means like that card is a king. So A, I can write real quick here, face card. B, king, right? So now let's do this one. P of A, let's test this formula. P of A, that means P of A at the bottom here. That means the probability of having a face card. That means 12 over 52. Are we good? And event of A and B, that means the face card and a king. So just 4 out of 52, right? 4 over 52. And the probability of having a king given that is a face card. Okay, So what do you think? When you take 4 over 52 divided by 12 over 52, so you have 4 over 12, which is 1 over 3, right? So given that the card is a face card, the probability that it is a king is 1/3. So that is the meaning of this example. Are we good? Good, right? Then let's do this example. Now, the example related to pre-employment drug screening. Find the following using the table. If one of the 555 test subjects is randomly selected, find the probability that the subject had a positive test result, given that the subject actually used drugs. That is 5p positive test result, given that subject used drugs in this case, right? And then you can use the formula. Okay, so let's use the formula here. It is, let me change to the red color. It is gonna be P of A and B divided by P of A, right? Which one is A, which one is B? Please remember the way to remember. This one is like, this is A, right? The bottom one is the one like on the right side, and this is B. So in this case, the bottom, let's calculate the probability of subject uses drugs. Subject uses drugs. How do you find that? Subject uses drugs. Let's look at this row. So you have 45 plus 5. These are the number of subjects who use drugs, right? You have 50. Do you agree with me? 50 divided by the total one of the 555 test subjects is randomly selected. Okay, the sample space is always 555. Now let's calculate A and B. The bottom is always 555, right? Because in this case, like we have the same sample space. And A and B here, that means let's find the number of positive test results in subject uses drugs. This is the not use drugs, right? Positive result. Look at this one. This is positive test result and subtract usage drug. So this is going to be at the intersection of these two both column and row here. So you have 45 over 555, right? So when you do the subtract the division, you're going to get 45 over 50. So that is the probability of getting positive test result given that subject uses drugs. Are we good? Good, right? Okay, let's do B. I'm gonna clear all my drawing here. So now B, let's find the probability that the subject uses drugs. So this is B, this is A. Given that positive test result, it means that you have to find like P of A and B divided by P of A. In this case, let's say P of A. Now let's find the number of the drug, the positive test results. This is the number of the positive test results, right? Do you agree with me? What do you think? So how many of them? 45 plus 25. So we have 70, right? And P of A and B, again, the sample space is 555. Now, let's find the number of subject uses drugs in positive test results. This is using drugs in positive test result. Again, it's still 45. Now we can do the calculation 45 divided by 70. So we are done. That is the answer for B. It's easy, right? Okay. I'm gonna wait to see if you have any questions here. And please remember, after doing the calculation, you have to do the interpretation, right? The first result of P positive test result, given that the subject uses drugs, is 0.900 indicates that, because the first answer we find, like, that is the answer for A, the question A is 0.900. So that's why when you do the interpretation, you mention it here. That one indicates that a subject who uses drugs has a 0.900 probability of getting a positive test results. That is the meaning of this number. And then you can do the interpretation for the question B. For the question B, what is our answer? It is 0.643, right? After calculation, you have this number. So this number indicates that for a subject who gets a positive test results, let's look at A here. This is the condition, right? Who gets a positive test result, there is a 0.643 probability that this subject actually uses drugs. So that is the meaning of the number when you do the conditional probability. And please note that when you switch these two positions, like the subject uses drugs and the positive test result, the probability will be different. They are totally different, because in general, this probability of the event B occurs, given that the event A already occurred, is different from the probability of the event A occurs, given that B already occurred. They are totally different. So this is just the confusion of the inverse, right? Some people may make mistake. They think that they are the same, but they are not actually. They are different. Now, let's consider these events. It is dark outdoors. M, it is midnight, right? So let's find. Uh, we can say the probability of the event, it is dark outdoor, given that it is midnight. It is one, because it is certain to be dark given that it is midnight, of course, right? Now the probability of the event, it is midnight given that it is dark outdoors, is 0, because the probability that it is exactly midnight given that it dark is almost 0. So in this case, this is an example to show that they are totally different. Confusion of the inverse occurs when we incorrectly switch those probability values or think that they are equal. Now, let's move to the main theorem. This is a very important theorem in probability theory, Bayes theorem. So what is the meaning of Bayes theorem? And I'm going to give you an example of Bayes theorem, okay? We extend the discussion of conditional probability to include applications of Bayes theorem in this case, which we use for revising a probability value based on addition information that is later obtained. I can firstly give you a simple example for Bayes theorem. Suppose there is a disease that affects like 1% of the population in a test. Okay, disease affects 1% of the population. And the test is 99% accurate. Now the question is, if someone tests positive, what is the probability that they actually have the disease? If someone tests positive, by the probability they actually have a disease. Okay, so how do we do that? Given that D is the person, D is the event, the person has the disease, right? And D bar is the event that the person does not have the disease. So this is one, it stands for disease, and then this one, the person does not have the disease. And plus maybe that stands for test is positive. Okay, so let's find from the problem. You know that the probability uh, that a person has the disease is 0.01 because 1% of the population has the disease, right? And the probability of D bar is 1 minus 0.01 is 0.99. Are we good? Because they are complement events. Now, let's find the probability, the probability uh, of the if they are actually have positive test, given that that person has the disease, right? And no, it's gonna be the vice versa. So we need to find like the probability that the person actually have the disease given that they have positive test. Okay, this is what we need to find. Now let me show you the formula for the Bayes theorem, and then we can apply that formula to find the result. Okay, the formula for the Bayes theorem, it is PD plus equals P plus D times P of D divided by, you have the multiplication, plus given D times P of D, and then the vice versa, plus the other one, P of positive D bar times P of D bar. So in this case, we have everything. We just need to plug it in here and then find the probability that the person actually have the disease given that they have a positive test, right? So now let's plug everything in here. Maybe let me clear this drawing right here, and then I can write out the answer. That is the formula for the Bayes theorem. You can use that most of the time. It's very important, so you have to remember that one. Equals, so now let's find the probability of the person have a positive result even that they have the disease is gonna be 0.99, right? Of course, times PD is going to be 0.01. We calculated it above here, divided by the bottom. Now the probability of a person having a positive result given that they have the disease is 0.99 times PD, so it's going to be 0.01, right? Plus now the probability of the person who have positive result given that they does not have a disease is going to be 0.01 times the probability of the person who doesn't have the disease is 0.99. Are we good? So now you can plug everything in here and you can calculate it. The answer is going to be 0.5. So the meaning here is even if the test is 99% accurate, a person who tests positive only has a 50% chance of actually having the disease because the disease is rare and false positives matter. So in this case, that is the meaning of the Bayes theorem. It helps us to calculate this example, right? So now it's gonna be your turn. You can practice with this example, and we have the solution in this slide already. If you have any other question, please feel free to email me, or you can schedule a meeting with me to ask me any question. Okay. Thank you, everyone. I'm gonna stop recording here. Stop sharing and stop recording.